Second one is we are going to see what is a filter, multi-stage, sorry, not this one, to chapter 2. Yes. So I'm going to filter a sequence. Okay, I'm going to filter a sequence. Okay, so see here, I'm going to generate a random signal and I'm going to add noise to it. See here, I'm going to take the sampling frequency as 8000 and I'm taking the, whenever you use a Gaussian variable, you have to define what is called as variance, right? So I'm going to define the variance and I'm going to take 0 to 200 is going to be my sample size. So I'm first creating a noise. I'm creating a noise. It's a Gaussian random noise. So I'm going to use the random function and I'm going to create a Gaussian random noise variable with the variance 0.00005. Variance has to be very, very less. And you see, I am going to add noise to the signal. This is your noise. I am going to add signal to this noise. So from 51 to 151. So totally, you see, the signal noise is having a length of 201. In that, I am going to add signal only in the later portion of the signal, 51 to 151. I'm going to add signal. Okay, now I'm going to filter this. I'm going to filter the thing with an FIR filter of order for 48 and the passband edge is 1000. So till 1000, your signal will be filtered. Okay, the edge is 1000. So till 1000, the signal will be allowed. After 1000, the signal will be stopped. Okay, that is what I'm doing. I am convoluting the input. Input is S and the filter coefficient is H. I'm performing convolution and I'm going to see what is the input and what is the output. This is a simple example of signal plus noise filtering. The previous case, we have filtered only the noise, right? Now we are going to filter the signal plus noise. Why we are adding signal plus noise means in any communication channel you go, the receiver will always receive the transmitted signal plus noise. Okay, that is the reason why I'm going to take signal plus noise here. We'll run this and see. See the input. This is the input. 51 to 151, I'm adding by signal. So 51 to 151, you can see the signal. Otherwise, it is random. From 51 to 151, I'll have my signal. This signal is looking like a sine wave. Okay, and after 51 to 151, again, I'll be having noise. And I'm going to filter this signal by a FIR filter. The FIR filter is ideally it will be like a delay filter. So it will add some delay to your input. After performing convolution, you can see the output. Output is very clear. See, at least in the signal portion, you can see the output is very clear. It is not having any variation. But see the input side, you are having random variations at every point, right? But output, you see, it is very, very clear. And the random portion, that is also being smoothened. That is the significance of filtering. Filtering is done to remove your noise. So whenever you have a random variation, you can go for filtering and you can remove the noise. And how you can increase the efficiency of filtering? By having filter order, which is going to be very, very high. So here I use filter order of 49. If assume I make it 200, you should get even more smooth signal. We'll see whether we are getting that. I think the filter order 200 is too much. You see, the delay is the delay is going to be very, very high. The FIR filters will filter your signal as well as they will add delay. Delay means the signal will be moving towards the right or left. You can see it is relatively very much smoother. Okay, so this is one example I want to show.